Okay, welcome back, everybody. This is the 2025 Virtual Residency Workshop. It is Tuesday, June 24th, or for our speakers, I believe it is now Wednesday, June 25th. So they are the seers of tomorrow, so they can tell us what the future looks like by a good 17 hours. And they are going to be speaking. So this is Wallace Chase and Aaron Murray, and they're going to be speaking today on research networking overview. And I'm going to go ahead and turn the show over to you all.
All right, thank you, Henry. Aaron, if you want to pop up the slides.
See if I can figure that out.
We ourselves are in two different locations, so we're coordinating this live in real time.
And there we go. That works. Ooh,
Yes, except the text
there
has, there we go, it filled in. Darn networks, always causing us problems. All right, good morning, everybody. So this is a discussion that is titled, and the title is on the program as "The Internet is Fine." I'm on Facebook right now, but I have been informed by a reliably younger colleague in Aaron that Facebook is old news and that you're on TikTok right now. I am on neither, so I will defer to his judgment of being in with whatever is hip on the interwebs right now, as I am definitely not. But this is a discussion around how networking that supports data-intensive research is not the same necessarily as networking that supports normal internet things such as browsing Facebook, using the web as most people do. All right, so we'll go on to the next slide here. So the question is that you may have, is this going to make you a network engineer by the end of this discussion? And on the next slide, no, it will not do that. But if we go to the next one, it will allow you to at least navigate the world of the network engineer and to kind of understand what they're going through. Even if what network engineers say sometimes it can be very confusing and not necessarily all just easy to understand. All right, so you need to know this because in supporting research computing, this is a very confusing, complicated world for the end user. If it's confusing for us, which it is as practitioners, it can be, you can only imagine what it looks like to the end user of trying to actually move a data set around the campus, around the nation, or around the world. Okay, next slide. All right, so just want to introduce myself and introduce all of you. Tena katoa, now my haramai my ki tenu hui. Just a welcome to this presentation and to the group here. My name is Wallace Chase, and I'm the head of Department for ITS at the University of Otago here in New Zealand. So that's on the South Island for those of you who know New Zealand, and I've been here about 7 years. Prior to that, I was with Clemson University in South Carolina, thus my accent is not very New Zealand-esque, and Washington State University, George Washington University in DC, and finally Lake Superior State University in the US. So all over the place there, always in central ITS, but always having a bent towards supporting research and making central ITS departments better at supporting the research needs on campuses. And I'll turn it over to Aaron to introduce himself.
Hey, yes, I'm Aaron Murray. So I'm technical lead for networks at REANZ. So REANZ is the Research and Education Network for New Zealand. I've been there since 2016, which is just far too long. But anyways, I before that I was sort of more of a standard network engineer at a wireless ISP delivering sort of rural internet services. Yeah, back to Wallace.
All right, yeah, and for those of you who don't know, RIANS is basically kind of the Internet 2 equivalent here in New Zealand, so for our American colleagues there. All right, so heading over to the next slide here. So let's talk for a minute about data and the differences in what normal people would consider a lot of data and what we in HPC and especially in advanced networking think of as large amounts of data. So if you are a typical home user, you may have a very large amount of Google Photos, you may have a very large amount of movies or something like that, and you think that that is a lot of data. And it can take sometimes quite a while to move that stuff around. If you've ever done an export, Google Takeout on your Google Photos folder to back it up, which you should do, by the way, if you're using that, it can take a very long time to download those files. They can be large. You'll notice that Google splits it up into multiple files that you download that are compressed and all that sort of stuff. Those are small amounts of data in the world that we're dealing in. We are often dealing in not only gigabytes, but terabytes and petabytes of data. And that can be quite a difference when it comes to actually moving that data around or manipulating that data, storing that data. I'm also in charge of data storage for the University of Otago. And we have about 40 odd petabytes or so. And that is quite a different thing to deal with than on the research side, we have about 40 petabytes. On the enterprise side, basically everything else in the university is under 1 petabyte. So it's a very different scale of data that you're talking about when you talk about computational research nowadays. Okay, so you have on the screen here kind of the different types of commodity and commercial networks that exist around the world. Just some examples here, some from New Zealand, some that will be familiar to those of you in the US. And those networks are the ones that you can go out and you can buy service at, if you're lucky, to be able to service your household. So you'll get a either fiber connection or DSL or phone line service, whatever you end up getting that's available in your area, cable, modems, and you're able to get that internet access in your house. However, if we go on to the next slide, research data is very different than the type of data that you're doing there. It's the equivalent of a wide load needing to go down the street. So you have a normal residential street or even a city street or highway or something like that, and it takes a lot of work to get these huge oversized loads through there. You see one basically taking up the entire intersection. You've got companies there moving power lines out of the way and traffic control and police and multiple trucks and specialized trailers and all that kind of thing. And that's really an equivalent to what we're dealing with when we deal with very large research data sets. So they can either be just very large oversized, or as this slide shows, it can be just a lot of data coming in a stream. It can be large amounts, heavy weights of data here that just continues to come and needs to flow. So that you can think of that as if you have an instrument or something like that, a telescope, a genomic sequencers, any of those types of instruments that are out there that are pumping out large amounts of data repeatedly that needs to be stored temporarily, processed, stored again, and all those decisions and stuff that happen with that. Also, keeping in mind that often research instruments are nowhere near where the computational resources are. So you may be getting data coming in from other places on the planet. We do quite a bit of work right now here in New Zealand with Antarctica, for instance, and moving data between the stations in Antarctica back to here. Right now, they have to put computation on the continent, on the ice down there, because it's hard to move large amounts of data. So there's all sorts of things that happen when you have the inability to shuffle that data around quite as efficiently. So if we go on to the next slide, one of the questions is, well, why can't those commodity or commercial networks handle the type of research data that we have? And I like to kind of sum it up in this slide. So if you're out to make money, you are going to want to be in that top bracket there, the commodity arrow, where you're putting in a certain amount of effort and you're getting a nice, big, juicy result out of that. For research and education networks, often we're putting in a ton of effort for a much smaller portion of the population, for a much smaller portion of the overall traffic on the internet, making it, quite frankly, just not commercially viable. So if we go to the next slide, this is a really good example, and this is from the U.S. Consumer Financial Protection Bureau. Has nothing to do with networking or HPC or anything like that, but I think this is a good indicator of diminishing returns. So these are consumer complaints that they get. So if you're somebody at the Consumer Financial Protection Bureau and you are understaffed, underpaid, all this sort of stuff, and you need to deal with complaints and make the service better, what are you going to do? Are you going to concentrate on the ones all the way over to the right? Or are you going to concentrate on the ones to the left where there's a lot of complaints about the same thing? And this is a pretty good analogy for what happens with commercial networks, those commodity commercial networks, is that they deal with the 90%. They're trying to deal with the most amount of traffic, get the most amount of customers, and they're not necessarily going to cater for those wide loads or those extreme ends of the data spectrum because they just don't deal with it that much. So incomes on the next slide, basically where state regional networks, particularly within the U.S. and all over the world, come into play. There's just a bunch of random logos there of ones that throughout the U.S. and some through and one in New Zealand there. But these are different networks out there that cater specifically for those large research needs. And there's a lot of special stuff that happens behind the scenes. So if we go on to the next slide, you guys know that I love analogies. I usually actually put a warning in my presentations about the number of analogies that were going to happen, so you just kind of have to deal with it. But both research networks and commodity networks, you think of them as both animals that are eating leaves and doing what kind of seems on the surface to be the same thing. But if we go to the next slide, you can find out that if you try to get one to do everything, you end up with an abomination that might just not make any sense or work very well. And the reason for that is on the next slide, it is all about making money when you're a commercial company providing internet access. That is what the world is about for you. You have shareholders, you have profits to make and that sort of thing. And it's just simply not profitable to deal with the relatively small amount of really big data customers out there. And we know that although there is a decent amount of money that does flow around the research and education space, that spending a ton of money on transport maybe isn't the thing that we want to do to incentivize these companies, but to be able to do this in the most efficient, effective manner possible. Now, if we go on to the next slide, we're going to talk now a little bit about more of the technical reasons that makes these two types of networks or these two types of network companies different between the research and education networks that exist around the world that support you in the university and HPC sector, and then the ones that support just normal home users. So if we move on to the next slide, it will take you way back to the beginnings of networking. Not even necessarily the beginnings of the internet, although this is a map of what you could kind of consider to be the first network / internet thing that started to come up, which was ARPANET way back in the early 70s. So when this was developed, when the internet was developed, it was really developed out of both research needs, but also out of the U.S. government. The U.S. military needed a way, move to the next slide, to be able to communicate in the case of a nuclear catastrophe, basically nuclear war. We need the ability to talk to each other, to send commands, to send things, to tell these guys when to turn the keys, that sort of stuff. And to do that, you need a highly resilient way of communication. And some of that was done through the phone line systems in the U.S. There's some fascinating documentaries out there about the different AT&T phone line systems that existed during the Cold War and how they were made resilient and the microwave networks and all that. But that's quickly started to become taken over or at least backed up by a version of the internet. And one of the key tenets in that was to make it extremely robust, basically, to be able to make it so that the network could work around any faults, parts of the network / country disappearing, that sort of thing, where traffic was able to go around. And so that turned us into a network that looks like the internet does today and kind of explains some of the backgrounds. I'll turn it over to Aaron to talk in more detail around that.
Yeah, thank you. So the internet, I mean, as we all are aware, is just a really big kind of interconnected system using really standardized protocols. The use of standardized protocols in this respect is really important because it's the only way we're actually able to sort of, at the scale that we're working at, we're able to kind of pass business logic and things between different institutions at a mega scale. At the absolute highest level, the internet looks like this, and that is not drilling into sort of the complexity of every individual network. This is just how kind of networks interconnect with each other. It is a hugely complex ecosystem. And every single network that exists on the internet, whether they be ISPs, whether they be RNE networks, whether they be end users and things like that, all have their own kind of engineering principles about how they run their own infrastructure. They have their own business logic, their own sort of fiscal concerns, and all of those sorts of things that bake in to make every single network, pretty unique. And as such, it's kind of really quite impossible to tell what path really your data is going to take across a network. So when that comes to doing diagnostics and things like that, it becomes hugely complex. In addition to that, actually, with more modern networks and things, a lot of what's actually happening within each network is completely hidden from you. You can your packet might enter, say, a telco, one of the big tier ones, and it just pops out the other side. It's probably hit 30 or 40 routers in the middle, but you never see that. So actually, how can you tell what your data is doing, where things are going wrong, and how to fix it? Essentially, if you just come in and try and look at how the internet works, it kind of just looks like magic. And no one can actually keep a full sort of view of what's happening in their own head. All they can do is focus on their own part of the infrastructure, make that work as best as possible, perhaps work with the people that are directly connected to you. But once it's beyond that, it is incredibly difficult to sort of achieve any meaningful change. So I just wanted to talk a little bit about how sort of the internet as a whole has changed over time. Just a very small amount. Originally, the internet was a very kind of decentralized network. That meant that services existed all over the place. You ran your own services, your own web page, web servers, your own chat rooms, your own email even, which was just a hideous thing to do. And over time, that's actually really changed. We've moved from a decentralized model of the internet to a much more centralized model. Now, the internet still kind of exists in a decentralized manner. That makes it really robust. That makes it really resistant to, nefarious actors, nation states, things like that, being able to take it offline. But that said, all of the content, all of how we use the internet has kind of moved into a very kind of centralized, you go to one place or half a dozen places to get, all of the data, all the content. They own your data. They, deliver the services and monopolize and make money and advertise and all of those sorts of things. And that kind of led to the rise of content delivery networks, where you kind of split the internet into a series of either content delivery networks, CDNs, or eyeball networks, which are essentially all of us at home who are looking for content, not necessarily creating content and providing it back to the ecosystem. And with a CDN, essentially what that's done is that takes all of the most popular data and kind of pushes it out to the edge as close to the quote unquote eyeballs as possible to get the best performance, to get the cheapest delivery of data, and all of those sorts of things. However, RNE infrastructure has remained mostly decentralized. And the reason for that is just where the content, the content that RNE networks deliver comes from, and where it needs to be delivered to. Scientific instrumentation is distributed all over the world. Obviously, a good chunk of it is in the US and in Europe, but it's distributed all over the world. There are data sovereignty sort of requirements, as well as privacy requirements around research data, especially around human research data. And there are really, really specialized data storage, as Wallace alluded to before, and compute requirements as well. And each research use case tends to be pretty unique, and this sort of means that using commodity services to deliver it can be really difficult, can be really expensive. So we tend to maintain our own infrastructure in this space. But that said, we can still leverage commodity services, cloud, things like that, where it makes sense to deliver what we need, because it can do it really cost effectively if we do it right. I'm going to move on a little bit towards talking kind of about behaviors of networks, and why R&E networks need to be designed a bit more uniquely than say a telco. Most data is transferred across the internet using a protocol called TCP, so Transmission Control Protocol. And typically, as Wallace stated, internet traffic tends to just be lots of really, really small kind of streams of data. You get it, you're done. It takes, half a second, maybe a couple of seconds if it needs to load up a particularly large amount of data. And then you move on, and you've just got hundreds of these things going all at the same time. And so actually running into issues with network infrastructure, internet infrastructure you don't tend to notice it that much. Browsers just reload, things just continue working if you run across any errors. With R&E infrastructure, we are talking about really long streams. There's a term for these called like elephant flows that can go for days and weeks. There's petabytes of data that needs to be transferred at high rates. So this is where sort of TCP comes in. TCP is essentially what most of the internet is built on. That is changing, but it basically gives you a reliable way of ensuring that data gets delivered from A to B, gets delivered correctly, and gets delivered in order. Now, there are three things that kind of impact TCP performance. The first one is latency. So that's how long it takes basically a request and a response to the other party that you're communicating with at the time. So probably a server, maybe a storage node, something like that. That's how long it takes for it to get there and back. And this is typically in milliseconds. If it's really close, it might be a handful of milliseconds, between 1 and 5. If you're going across to the other side of the world, you may be talking like 2 or 3 or even 400 milliseconds. The other thing is TCP window size, and that's basically how much data you can have, or your kernel will push onto the wire at any point in time, and basically how much data it will have in flight at any point in time. And the third thing is packet loss. And all of these are interrelated a little bit, and it's actually really important that these behaviors are kind of understood at a high level. You don't need to delve into the specifics, although I will delve in a little bit, although I'll try and not go too far. But it's really important to understand kind of how this works at a high level, so you can understand where your bottlenecks might be when you're trying to transmit lots and lots of data. So the first one is the bandwidth delay product. You can Google it. There's a Wikipedia page for it. It's a really, really well understood problem, and it's actually really simple. Basically, the amount of bandwidth you can get out of any connection is limited by your TCP window size. That's how much bandwidth you can, how much data you can get on the wire at any point in time, plus times the latency of that link, and basically, compared to the latency of that link. And if your TCP window size is not large enough, then essentially you have a whole lot of wasted space while you're waiting for acknowledgements for that data to come back. You get far better performance if you fill out essentially the entire length of the round trip time, of the latency of the link, with data to ensure that you are getting as much performance as possible. And then on top of that, it gets a lot more complicated when you start adding loss into the connection. Now, things that can introduce loss, the main one that people think of is congested links, and that is a big one. But there's actually other types of other ways you can introduce loss. There could be the medium that you're transmitting data across. So if you're connected to Wi-Fi, a bit of interference is going to create a large amount of loss. Other things like hardware failure. One of the big ones that we see are faulty optics, and they just start erroring every so often. Light levels start to drop. And that's why we need to be really on top of those sorts of failure modes to ensure we get failed hardware swapped out as quickly as possible. But that can occur, and it won't necessarily be a going from working to not working. It can just be intermittent loss being introduced as hundreds of thousands, millions, billions of packets are being sent across that link. And the other one is oversubscribed hardware, essentially. Basically, modern day routers are actually really capable of just forwarding packets really, really well. It's when you introduce a bit more smarts, quote unquote smarts to those devices, where actually you can just start losing packets, even if there's not necessarily large amounts of data that needs to go through. Examples of these are generally, perimeter edge firewalls and things like that are doing a lot of data inspection, SSL inspection potentially, although hopefully not, and those sorts of things where they can run out of memory, they run out of CPU because it's all done in general purpose compute on those devices. And they can run out of that capability and just throw packets away instead of forwarding them. So I just wanted to talk a little bit about how TCP behaves when you sort of introduce loss into a connection. TCP under the hood runs an algorithm, one of a number of algorithms. I'm not really going to call out what the algorithms are, but basically it's about how they handle loss and back off. Back in the day, loss was assumed to have been caused by congested links. And so you wanted your TCP stream to understand when it hit a congested link so it could back off, so it could be a good internet citizen. But with other things introducing loss, this can actually create a lot of issues with performance, because the way TCP works is you ramp up as quickly as possible by basically doubling your speed each round trip time until it hits loss, and then it backs off, and then it starts ramping up again to see if that sort of congestion has disappeared and backs off. And so if you're getting a lot of kind of random loss, you end up backing off your TCP stream a lot, and this really, really hampers your performance. So where on the network is loss likely to occur? And this is just kind of my anecdotal experience of where I would expect to find loss. If I'm pinging from A to B, or I've got an application that's telling me that I have loss on my data transfer, this is typically where I would look for loss occurring in this order. The first one is, how is your device connected to the network? A lot of people will start transferring, it'll be on Wi-Fi, the Wi-Fi is not great, and they're just getting really poor performance. And to be honest, the easiest thing you can do is just plug the thing in, and a lot of the time problems go away. Beyond that, services could be experiencing issues. And so it's worthwhile having a look on that service web page, or if you're working with a colleague, having a chat with them and seeing if they're experiencing issues. Beyond that, the firewall, the perimeter edge firewall of your institution, or depending on what it looks like on the other end, the institution at the other end as well. And these things, usually you can tell when losses are occurring across these, because you can run things like a trace route, you can see loss on particular hops, and so you can see that. Although that said, there are a lot of caveats to using trace route as a diagnostic tool. If inevitably it's going across the general internet. Look, that I mean, it's quite likely loss is being introduced there, although we are a lot better these days, unless you are doing a lot of data. But if it is across the general internet, it's just really difficult to track that down. I've sent emails to Verizon before, and you just can't get responses from them. If it stays within kind of domestic New Zealand, for example, it's a really small community. We've got a Slack channel. I can reach out. It's really easy. But once you go into the global community, it's basically impossible to do. To track down where issues are, to either get them fixed. The easiest thing to do is figure out how to avoid it. Probably the fifth most likely is the campus LAN. This is especially likely if hardware on a campus LAN is kind of reaching end of life, and they're just kind of holding on and sweating the investment before they can get the funding to replace it and ramp up its speed from 10 to 100 gig or 100 gig to 400 gig or whatever it looks like, depending on the size of the institution. And finally, look, we do end up with issues inside of R&E networks. If we didn't, I wouldn't have a job. Yeah, and we're usually, R&E networks tend to be, because of the function that we serve within the research and education ecosystem, we are really careful about ensuring that monitoring is in place, that reporting is in place, so that we know there are issues, particularly issues like packet loss, before even you do. We have at REANS, we have an alert that goes off if we experience any errors or any discards on any of our backbone links, because that means it's oversubscribed and potentially we're not delivering the value and the impact that we need to for our own member institutions. I have put us last in this list, but that is not to say you have to exhaust all other avenues before you actually talk to us. Us being the global, whoever your R&E network is, reach out in the first instance. Obviously, check what your connection is, check the guy on the other side, probably check in with your ITS, make sure that they've got no issues. Otherwise, getting your researchers or yourselves or your ITS to get in touch with your R&E network, depending on what that relationship looks like, to continue helping the diagnostics. Because although they might not be generally responsible for the fault, they certainly have experts that can really help you diagnose these network issues. So when you do have network issues, so I've got a graph here of kind of the expected behavior of a data transfer using TCP, with certain sort of variables changed. These are not 100% accurate. This is just an online calculator. It actually tends to take the pessimistically worst case because it tends to apply evenly spread out loss, which isn't actually really what happens in the real world. And actually bursty loss gives you better performance than evenly spaced loss, just because of the behaviors of TCP. But basically, as latency increases, loss becomes more and more impactful. So that orange line there basically just says there's no loss at all. We've got a window size of 100 meg. And so basically you don't end up falling off performance until you're up at around 50 to 100 milliseconds of latency. At that point, you need to potentially take some special steps to improve your performance, which I'll get into shortly. But as you can see from the green line, and that's our kind of best case with a little bit of loss. So that is there with 1 in a million packets going missing. So just 1 in a million. When you're really close, you can still get full speed. But as soon as you're kind of delivering across a city or delivering into a different state, the performance just absolutely tanks. And so that just shows you sort of how much a really small amount of loss, or like a 1 in a million packets, can really impact performance. That blue line there actually is just 10 times as much. So I just wanted to sort of show what 1 in a million versus 1 in 100,000 packets does. I think that's right. Yeah, that's right. And it's significantly worse. Obviously, even within the same rack, you'll get pretty poor performance when you're trying to transmit at 10 or more gigs. And finally, at the bottom there, I just added this is kind of how the internet used to run back in the 2000s, where operating systems just had a bog standard 64K window size. Even with no loss, you just can't get good performance through it. It was fine back in the day because you just couldn't transmit at 10 gig. It just didn't really exist. So it wasn't too much of an issue, but as networks have gotten faster, operating systems have had to modernize, have had to take some steps to actually improve their window sizes to ensure that we can actually make use of our full capacity. And so that leads me to the slide of actually, we've discovered we've got a problem. We need to figure out what that problem is. And if we've figured out what that problem is, what our bottleneck is, what steps can we actually take to mitigate that as an end user, not as necessarily someone sitting in the middle causing the problems. And the first one is, as I've been talking about, increasing your TCP window size. Now, fortunately, modern operating systems now actually auto scale their window size. So it used to be, bog standard 64K windows, but now they'll actually scale up all the way up to, I think, a gig as default, as needed, although they generally don't get that high, although for research purposes, they probably will. Scales it all the way up so that you can get the performance you need, and it kind of just does that a bit dynamically. The easiest thing that you can do is actually go from one TCP stream to multiple TCP streams, because if the loss is not being caused by congestion, then kind of the intermittent loss and the play on TCP and the sawtoothing that we saw in that graph, you usually offset it, and you can kind of get a higher base level of performance across multiple TCP streams. Usually 5 to 10. 10 is pushing it. You don't usually want to go beyond 10 because you run into other issues. But say 5 simultaneous TCP streams can give you a really good performance boost depending on the performance bottleneck. And most transmission applications will give you a way to do this, although not generally bog standard web applications. The other thing you can do is avoid lossy segments. Obviously, if you have a problem with one ISP and maybe you've got a redundant ISP, you can fail over to the redundant ISP and actually see if those problems still occur. If you can't do that, then you're just going to have to reach out to your ISP and see if they can reach out to whoever is causing those issues. Another thing you can do is actually change your TCP control algorithm. Now, these things are baked into the kernel, so you can't actually, well, you can invent your own one. It's hideously complex. You have to roll your own kernel, but there are a number of different TCP control algorithms inside, baked into the kernel, which you can change to. Typically, the one that we run today, which is Cubic in Linux. I'm not sure if Windows runs that or something different. It works pretty well. These TCP control algorithms are designed to be kind of really good internet citizens, so they're not smashing links that are congested. But there are other types of congestion control algorithms like BBR, which I've got there, which was developed by Google, which is a really good internet citizen when it's working with BBR, so when the rest of the network is running BBR as well. But if the rest of it's running, for example, standard Cubic, something like that, it will stomp all over them, which is not good as from an internet citizen perspective or a network citizen perspective. But if you really want to get performance on your applications, then just switch to BBR and you'll get the best you possibly can. The other thing you can do is swap to UDP based transfers. This is it's an okay solution to the problem. You still have, essentially what you're doing is you're solving your congestion control in UDP, which means you can solve it in user space, which means it's much easier to make changes to that than inside of the kernel of your operating system. Some transmission applications will allow you to do this. They'll run their own acknowledgement and congestion control algorithms, or maybe no congestion control, just send it as fast as you can and then just receive ACKs for anything that made it successfully. And another thing you can do is enable jumbo frames. This is more around if your servers are not able to send data fast enough. You can usually enable jumbo frames, because what that'll do is that'll reduce the computational overhead of the kernel creating packets, so you can get more data for less kind of encapsulation work that the operating system has to do. Most NRENs will run a native 9K network, MTU network, so you can work with them to stand that up. And in some instances, it might help your performance. So I'll talk a little bit about kind of the different levels of networks. So that's your LAN, so your local area network, your metro area network, and your wide area network. I won't dwell on it for too long, but it just kind of shows how networks increase in complexity as sort of the size increases. So your LAN is typically just a very small section of network. It might be one or two, handful of layer twos. It's a bit of switching. There'll be one router, and it's got anywhere from a handful to a couple of dozen to maybe a few hundred machines behind it. And that all exists within a very small kind of geographical area. Yeah, you can tie a couple of these LANs together, plugged into a router. And then you move on to sort of the metro area networks. And this is where you kind of define the network by a larger geographical area, something like a university campus, within a city, or maybe even several university campuses within a city. They all get tied together. And so that's a series of LANs that all get tied together into sort of this metro area network, and there's a lot of routing going on between them. And then you run into the WAN, and the WAN is very much a larger geographical area. So this might be every campus that a university has all tied together into a single network. Typically, you're not going to be rolling your own infrastructure to deliver connectivity between all of these. You're going to purchase that as a service off someone else. Although that said, in the States, you guys do things differently there. And a number of the sort of the regional R&E networks or state networks are actually just universities running their own infrastructures to deliver their own WAN services, and then kind of on-selling or delivering those services to other institutions to make use of as well. Yeah, and as Wallace said before, look, these things are complicated, really complicated. It's your guys' jobs to sort of understand that these problems occur, not necessarily how to fix them, but know who to reach out to actually solve problems as they crop up. Wallace.
Yeah, thanks for that, Aaron. We did have a question come in while you were talking, which we'll take right now if you don't mind.
Yep.
So the question was about robustness and how many root DNS servers are there these days, and are most of them still in the US, or has that changed?
So that's definitely changed. Look, the rest of the world doesn't particularly want to be beholden to individual countries that are not their own to deliver, critical internet services. So there are, I think, A to H. So what's that? 12 something 11 root DNS name servers, but that's root DNS name server zones. Each zone tends to have, from dozens to 100 or to hundreds of root name servers all over the world. We've actually just stood up at Reans. It's not to H because we've just stood up the mroot an instance of the mroot server in our own infrastructure to ensure that New Zealand has a root DNS server, which adds to the robustness of the global ecosystem, but also adds to the robustness of New Zealand itself. We can rely on a service within New Zealand to deliver our critical sort of DNS infrastructure. So I will say there is, I think, 13 root servers or root zones, and inside of each root zone, there is dozens to hundreds of instances of that root zone all over the world.
All right, thanks, Aaron. I had another question come in around TCP, and I'll read it verbatim here. So TCP is bad, and that is one would expect from almost a half-century-old technology. I'll counter that slightly here in my own words that TCP is a half-century-old technology, and I think it's working remarkably well considering it's a half-century-old technology. All other technologies went through a roller coaster. Why there has been nothing to replace TCP so far?
It's not that there's nothing that's obviously Quick is gaining a lot of prominence globally. So Quick is a UDP-based protocol. It's kind of a Web 2.0 type transmission protocol. It actually bakes in TLS encryption by default, and so it saves a bunch of time because it simultaneously does a whole lot of work around that TCP handshake, standing up TLS in order to deliver services. Really, the reason why Quick was invented was because Google wanted to make changes to how wanted to make changes to congestion control algorithms and things like that without actually having to update the kernels of every operating system of every client that they're working on. And so that's sort of why Quick has come to the fore. It's nothing to do with UDP being better than TCP necessarily. It's more about how easy it is to make changes to those algorithms that control transmission. I think TCP works extremely, extremely well, particularly with really small, numerous TCP streams that you see on the internet today. It actually works really well. It just doesn't work especially well for our purposes around delivering really large scale, network services or data transfers. Yeah, I'm not sure if that sort of answered that question.
Yeah, I would say that keep in mind too that the very decentralized nature of the internet, and although things have become more centralized in CDNs and the way that content is delivered and that, there are still hundreds of thousands of providers providing networks and internet service around the world. They're using every vendor that has ever existed. They're using pieces in their networks that go back to the 80s all the way to things that just got replaced yesterday. So it's one of those things. Once a very foundational protocol like TCP takes hold, it's kind of the same with Ethernet. There have been better things that have come along that work better than Ethernet, but because Ethernet got the adoption and is now everywhere, changing it's not like there's one company or one entity that can go out there and say we're going to change this, because it's literally hundreds of thousands of networks all over the world, from my network at the University of Otago to my network at home to Aaron's network that runs for New Zealand to everything else. So it's one of those things that once it takes hold, it's pretty hard to hard to strip it out. I think in networking we've seen the same thing with IP version 4 for folks who are familiar with that, and IP version 6. IP version 6 has been out for a long time. There's doom and gloom with IP4 version 4. There's not enough of it. There's all sorts of issues with it. IP version 6 is superior in all sorts of ways. But 20 some years on, it still has very limited take up in a lot of places in the world, simply because the other still works and there's workarounds and there's all these things, and it's just so deeply embedded in the technology stack. So I would say that TCP, yeah, doesn't work great for what we're doing necessarily, but still works pretty good for the rest of the internet, for that 99% of things out there. Um, and so yeah,
Yeah,
it's be around for a long time.
yeah, I think you're right in that it goes back to that argument of, the internet is so large and so complicated that the only way you can actually run a relatively performant global infrastructure is to have those really standard ways of doing things. And so changing those standards becomes really, really difficult. And also, if you introduce a new standard that ends up being a bit of a bully on the infrastructure, it's not a particularly good internet citizen, then actually that kind of, you might get a small performance bump for a period of time until everyone else realizes they have to do it and start deploying their own. And suddenly, we just have a really, really poorly performing infrastructure globally.
I think that's a really good segue into what I'm about to talk to next, which is what happens when research traffic hits normal networks. And some folks will recognize this particular picture. If you go to the next page, you'll know you might recognize it even more there, as far as that. And this is a good illustration of what happens when research network traffic hits regular networks often. There's just not enough headroom for it. Everything gets slowed down. The people on the road who are just fine going under this bridge then get slowed down because we've jammed up the network with the research traffic, that sort of thing. A kind of funny thing about this bridge is a couple of years ago, they spent about $500,000 to raise it up to 12 feet, 8 inches or something like that, which they thought was going to be fine. Within 5 days, a truck had wedged itself under the new bridge after spending $500,000 raising it up. So I think that's also a good analogy for the fact that, good engineering can't necessarily fix all end user initiated issues in the world. So talk about that. All right, so moving on to the next slide here. You can have very adverse consequences. So you get performance issues for the researchers, performance issues for everyone else as the researcher clogs everything up. Researcher gets frustrated, everyone else gets frustrated, everybody takes their frustration out on the poor IT staff who have no money and no time to deal with that. So as we move on to the next slide, what often happens? So people need to get their research done. They figure out a way around it. And this is one of these things that we really, really want to avoid. And one of the reasons why research networking and all the investment has gone into not only the global and national and state research networks, but also to really school up network engineers within research heavy institutions to be able to help. So what we don't want is we don't want that data to get put on a hard drive or a flash drive, packaged up in a box, and sent via the high latency, large amounts of bandwidth carrier that is FedEx, UPS, one of those DHL carriers. So there's all sorts of obvious issues with that, including security of the data and all sorts of other things there. And we really just don't want that to happen. Although there are still cases where it does make more sense to stick it onto a physical medium and ship it. There's some interesting cases that have been done out there of how much you can actually transmit and how fast via this method if you're dealing with truly massive amounts of data. And a lot of those research projects on the South Pole, for instance, do it this way. They'll package it up and it ends up on a C-130 that flies back to Christchurch, New Zealand once or twice a year and then gets shipped back to the US. And that's still better than some of the satellite links, for instance, that exist down in that area. So go on to the next slide here. The question is how can we overcome this? How can we make this work? And hopefully by this point in the presentation, you've got a little bit of an idea on how this can actually work. But Aaron's going to give you some details as to exactly how we in the community have worked around these issues.
Cool. Yeah, I'm just looking at the time, so we'll make sure we get through these slides relatively quickly. I think Wallace and I have been waffling on for too long.
That never happened.
Basically, yeah, we can sort of deliver the performance requirements necessary for research purposes by delivering specialized infrastructure for that. That is, as we've been talking about, R&E networks. So that's regional R&E networks, or national, or even sort of conglomerates like Géant, and although it is national internet too. But also internally in your own institutions, there's some steps that you can take, and Science DMZ is an example of one of those kind of really specialty type networks. Now, the thing about Science DMZ is it's not really a thing. It's kind of just a set of engineering principles, which I'll talk into a little bit more. It's made up of essentially, the basic parts of a Science DMZ is your data transfer node. Your data transfer node has, obviously access to all of the data. It's got really robust authentication and authorization capabilities to ensure that you're only able to access the data that you want. And it's got, really performant sort of capabilities of taking data from rest off disk and then putting it onto the wire at the speeds that you need, which might be 10, might be 100 gig, might even be more in some cases that I've seen inside of the States and Europe. Obviously, storage has to be really performant, and large amounts of storage. University of Otago on a global scale is a relatively small university, as is our second largest one, but on a global scale, it's relatively small. And it's got 40 petabytes of research data that potentially needs to be transmitted. Obviously, hopefully not all at once, because that's going to take a really long time on our 100 gig backbone. But portions of that need to be transmitted relatively frequently. And then research and education network. So that's a specialized network that essentially sits far less utilized in the normal case, so that when a really large science use case crops up, it's able to scale up and pass that data as needed. So this is kind of an example of what a Science DMZ looks like. Basically, it is taking your high performance infrastructure and just shunting it off to the side away from your enterprise infrastructure, because all you do when you put your very expensive high performance infrastructure behind your enterprise infrastructure, your enterprise firewall and things like that, is you just turn it into a really expensive low performance infrastructure. So essentially, one of the big things that you want to do is you want to get that Science DMZ, so that connection to your infrastructure, as close to your local R&E network as possible. Ideally, a dedicated connection straight into their routers. That's like the gold standard, but you potentially have to pay for extra fiber and things to deliver that. So plugging it into sort of your border router, and then having that delivered as a separate service straight into your R&E is usually a pretty good compromise there. One of the big things, and although this diagram does show a firewall for your Science DMZ network, it's not actually a firewall. You never want to put a stateful firewall in front of, you certainly don't want to put a stateful firewall with all of your enterprising knobs and whistles enabled that does all of the packet inspections and things like that, because there's just very little value in doing that. All of the data should be encrypted as it's being shipped, so that's not going to be useful. All it's going to do is it's going to slow down the data transfer. So usually what you'd implement as a security access control is probably like a set of ACLs, so stateless ACLs on the on a router, whether that is getting your R&E network to implement that for you, whether that's you implementing that on one of your switches or routers, and in addition to that, obviously host-based firewalls on your infrastructure. Usually when you're doing data transfers, large-scale data transfers, you for the most part know where that's going to go, and so you can actually apply relatively strict ACLs to ensure that in the first instance, your science infrastructure can only ever be accessed from the institutions that you want it to be accessed from. You can dial it down more than that if you want to, but one of the really nice things about stateless ACLs is they're really, really performant because you can run them line rate, hundreds and hundreds of gigs if you want. All modern routers and switches will do that today. Yeah, I think that's that. Wallace.
All right. So all of this is to say that one of the big points we want to get across here is that relationships make the packets flow. So there's a bunch of people out there in the networking community that can help you guys out if you're in the HPC community or in the research community in general to figure out how to make data transfers work better. I've numerous times in my career, too many to count, I've ended up sitting in a research lab with some researchers, and they've been talking about how incredibly slow their data transfers are, but they've never actually asked for help. They've never actually considered that it could be better than that, or that they're shipping hard drives around, and they've never even bothered to reach out. And some of that is our fault in central IT. We're terrible at responding sometimes to those unique requirements. You put in a ticket through the help desk, it gets lost long before it ever gets to the person and the senior engineer who knows about the research end of stuff. And hopefully some of us are getting better at that. But as I said, you as research facilitators really can help make these relationships happen. Know who it is on the networking team that can help with this. Know your contacts at your local research network, that sort of thing, so that you can actually help your folks out in this. So let's go through just real quick a couple of examples of what that is. So we've got different kind of tiers in the ecosystem here of research networks. So we've got in the US and in many countries, we've got state or regional networks. So those will service a portion of the country, or in the US case, a state may have one that is funded. And they are often directly connecting to institutions. So this is probably the closest network to your institution, if that makes sense. So going on to the next slide, here's an example of the Merit network in Michigan. Has infrastructure throughout the state, connecting most, if not all, of the higher education institutions and research-heavy institutions in the state together, and then all linking into the national networks, which will go on to the next slide here, which in the US, there are several. So there is Internet 2, which is kind of that broad overarching network that most of you will interact with. But then there's also very specialty national networks with NOAA and with the Energy Sciences Network out of Department of Energy. So there's some very specialty ones as well, that depending what your researchers are, they may be dealing with these different networks. On the next slide here, we can see that Internet 2 network is pretty broad across the US, has many different points of connection, and connects into and helps all those local regional networks connect to each other. So if we go on to the next slide there, we'll see this is a picture of the ES network, the Energy Sciences Network there. So again, another large network that goes across the country, mostly connecting those national laboratories together. But then again, there's a lot of universities in the US that collaborate directly with those national labs as well. So next page, you'll see N-Wave network, which is NOAA's. And then if we go to the next slide, we can see the kind of the next thing here, which is exchanges and POPs, or point of presence. So these are another subset of the ecosystem across the world, and these are places where a lot of these big networks, whether it's state networks, regional networks, sometimes university networks themselves, will connect in together all at these points. So there'll be points on the map where everything kind of connects together in an area, then spiders out from there. And those they'll often be those points as well for those international connections for the country. So there'll be places within the country where those international links come in. So if you go to the next slide here, this is kind of a really cool map coming out of the Quilt network in the US that kind of just shows all those different state networks and regional networks, how they interconnect together with Internet 2, and then you can also see some of those major peering sites on there, which would be those POPs or exchanges. There's a lot of investment in here. There's a lot of resource out here to help researchers move stuff around, especially in the US and in other countries as well. And to talk more about the international landscape, I'll turn it back over to Aaron to talk about national and international networks.
Yeah, so national networks are actually kind of, so national RNA networks are not actually that dissimilar to sort of your state level networks. In fact, um, it's sort of a mash of your, generally across the globe is a mash of your state level networks and internet 2 type thing, where we are actually delivering connectivity directly to institutions. We're delivering WAN services, internet services, NREN services across that infrastructure, but we're also managing the connectivity into the global ecosystem, which we'll go through a little bit more later. It's actually Internet 2 and Géant themselves are relatively unique. So Géant is in Europe. These two institutions are relatively, or networks are relatively unique in that they are not generally connecting direct institutions. They are connecting R&E networks together and connecting R&E networks to the rest of the world. So that occurs in the US, that occurs in Europe, but everywhere else, your national NRENs are doing the whole lot essentially. So this is just a quick map of sort of what the REANS network looks like here in New Zealand. Not too exciting. It looks pretty similar to the rest of what you'll see. But what you can see there is kind of those international submarine cables to get actually to Australia and to the US to actually connect into the wider ecosystem. Again, looks very quite similar to sort of your state level RNE networks is you've got Australia there and Canary, so that's Canada, although I'm sure you can recognize that. And yeah, this is just sort of illustrating a submarine cable that REANS uses to connect to the globe. So we've got connectivity into Australia, where we connect into internet resources, as well as ARNet, who's the RNE network for Australia. We've got connectivity across to Hawaii, where we connect into the University of Hawaii, but also then across to Seattle eventually, where we have a POP and we plug into Pacific Northwest Gigapop. Yeah, and essentially the idea is the each individual NREN connects into the global RNE infrastructure, which creates sort of this global high performance network connectivity. There's some politics around that. It doesn't work as beautifully as you like, because there's funding issues and passing data for other countries can get really expensive, but for the most part it works really, really well. For example, Internet 2 actually provides REANS connectivity or peering across to Europe, where we can plug into Géant and connect into European institutions there. We're also on Transpac out of Seattle, out of the Pacific Northwest Gigapop, that gets us across to Asia as well. And the other thing I wanted to talk about is kind of in addition, or as a part of the global RNE network, the global RNE network kind of wants to be greater than the sum of each of its parts. And so one of the ways we achieve that is by creating these groups of RNE networks who have a special relationship with each other, where they can do things. For example, APONet here, where we kind of agree to mutually back each other up across the Pacific. That way, each institution can save, significant amounts of money purchasing a lot of backup capacity, when actually they can just rely on another NREN to deliver that backup capacity. So REANS being very small and out of the way, we actually make pretty good use of this. University of Hawaii delivers us backup capacity into Guam, as well as actually backup capacity into LA. And ARNet provides us backup capacity from Seattle back to Australia on their infrastructure. So yeah, we've really benefited from this, and we do appreciate that. We in turn have provided backup capacity, or do provide backup capacity to the University of Hawaii, who had actually had a couple of cable cuts recently, and were required to use us to back up their international connectivity, which is really good for us to be able to give back to the community. Wallace.
All right, so I'm just going to take us through just a real quick example of this, and this is fictional. And if there's any network engineers out there and want to come at me with no, the traffic wouldn't go that way for this thing, well, things change all the time, and this is a fictional example just to show. So you can still come at me, but I might laugh at you a little bit. So, anyways, but I appreciate your passion. All right, so we've got 2 points here. Let's just say we're going from the University of Oklahoma to University of Otago in New Zealand. We've got some researchers that need to move data back and forth. So going on to the next slide here, we can see, so one of the first organizations that'll need to be involved in that is, of course, the IT group at the University of Oklahoma. They need to be involved in that transfer of data because it's going to first go over their local network. So going on to the next slide here, as soon as it leaves the University of Oklahoma, it's going to hit a network that's called OneNet, which is Oklahoma's research and education network, that then spiders across the state of Oklahoma and then provides that connectivity out from there. So going on to the next slide, Oklahoma itself connects into the Great Plains network, which is basically a conglomeration of connecting point for networks in that portion of the country that then provides one of those pops or those those locations where things interconnect. So after you get there, you'll go to the next slide, which will bring you into the Internet 2 network, which allows that traffic to transit the U.S., in this case, probably heading towards the West Coast to go out over the Pacific, which on the next slide, you can see where that interconnection point is at Pacific Wave. And that's in conjunction with the Scenic, which is the regional network for California, and the Pacific Northwest Gigapop. You have the Pacific Wave platform, which provides that connectivity throughout the Pacific primarily, but also across the country with some other international links. So if we go on to the next slide here, you can see that not only then you have the Pacific Wave, but you also have the PIREN network, which is the Pacific Islands network, which provides connectivity throughout the Pacific Islands. One place of which is New Zealand as well, that is connected into that. Now we're hitting Aaron's home turf here in New Zealand, so I'll turn it back over to him to talk about what happens once it hits New Zealand's shores.
Yeah, so basically that data will likely hand over to us at on PackWave, so at the Pacific Northwest Gigapop in Seattle. As you can see, we need to somehow get it from there down to DUD, the Dunedin site. And this is the path, actually, I checked yesterday. This is the path that it will, at the moment, take through the network. You won't see any of this because it's all kind of hidden away with underlay and overlay networks. But essentially what happens is it will jump onto our Hawaii cable system connectivity, which will then go through the University of Hawaii, sorry, not the University of Hawaii, a router that we have in a rack owned by the University of Hawaii, and then back to New Zealand, where it ultimately ends up in Auckland. And then from Auckland, it will follow the western side, the eastern side of our 100 gig ladder down the country, all the way, as you can see, to the University of Otago in Dunedin. Wallace.
Yeah, absolutely. So once we're at the University of Otago in Dunedin, you've of course got to get then through my network, and my network engineers will shepherd that data around. This is a really good example, though, of just how many organizations are involved in making that one research data transfer happen. And this is also the power of the RNE network situation that exists within the world today, is that either myself or Aaron can reach out to any of these organizations, and there's somebody there who will be there to figure out what's going on and to help make this data transfer a success. If we're going over the normal internet, nobody's going to answer our phone call, nobody's going to care. And in fact, even figuring out how the data flowed it may be almost impossible because it's just going to go wherever the internet companies basically have an open market for traffic and they barter with each other for who's going to transit what and different, who's the lowest price and all that kind of stuff. So here we can do defined paths, we can do specialty things, we can get those wide loads of those freight trains full of data through from one end to another, and there'll be somebody at every step of the way to help figure out problems when they exist. All right, so going on to the next slide here, I'll turn it back over to Aaron for just a second to talk about the many other things that exist within this community that help out researchers.
Yeah, so I mean, obviously the global R&E community kind of kicked off as a mechanism for getting data from A to B across the globe in a really performant way. But it's branched out beyond that, R&E, so they're still called R&E networks, but that's kind of a misnomer at this point. It's really around allowing or ensuring that we can make global collaboration happen. And so in addition to that, we've got certain types of applications and services and capabilities that the R&E community delivers on top of that. The big ones for those are Eduroam, which enables connectivity globally. I did quite enjoy being able to fly into Switzerland, and immediately my phone was connected to Eduroam. I didn't have to go and buy a SIM card, and it all just kind of chugged along. In addition to that, EduGain. So basically, it's a global kind of identity federation or a federation of federations, which allows us to ensure that researchers can be authenticated in a secure and meaningful way to provide access within our infrastructure to researchers from other countries and other locations. And so that global federation really enables collaboration between institutions, access to scientific infrastructure, access to data, access to libraries, and those sorts of things. In addition, the R&E community globally has created different types of open source, generally softwares and services that allow that sort of enable use of or enable better ways of doing research or delivering data, as is the case of FileSender, ensuring networks are performing to standard, as is Persona, or ensuring that there is secure access to things in the case of EduVPN. Currently, the sort of the global NREN community is investigating how we can collaborate on achieving security outcomes. These are, threat sharing applications or potentially mutual type threat management, threat investigation, kind of follow the sun type services. So we're working through this at the moment. Obviously, REANS is very small and out of the way, but we're trying to get involved in any way we can. But we are certainly keenly following what the much bigger folk like Internet 2 and the US R&E community, as well as the European R&E communities, are working through.
All right, so what does all this mean for you guys? And there's just a couple simple points here to reiterate that the requirements of a data-intensive researcher are very different than what is traditionally served for even on a university network. So you just need to be aware of that and reach out. So networks interconnect to networks to networks to networks. It can be very complex, but it does make sense to understand what your situation is, especially in the global R&E community, research network community is. Where are you at? Who are you connected to, at least in that first hop? Networks get exponentially more complex through as things go on, and NRENs are at the core of an international community supporting this. There's people there to help, and we just need you to ask and reach out when those kind of things are there. Research networks are there for you and for your data transfers. We can offer, the engineers will always look to help to support that going forward. All right, so in the next slide, I'll just sum it up again. So our goal is to make researchers like that Velociraptor with the RPG riding a shark, being able to go out there and do what they need to do, fearing no one. But there's a slightly different version of this for New Zealand. So we go on the next slide, and that is the laser kiwi. So we hope that our researchers here in New Zealand are like the laser kiwi, taking on all evils there. So with the last slide, I want to thank you all for your time today and listening to us blather on about something we're quite passionate about. If there are any questions, be sure to reach out. You can either put them in the chat now or just unmute yourself and talk now, or just reach out to either one of us on our email addresses. We'd be very happy to chat about this. Just watch out because we will chat about it. So careful what you ask for, you'll get it. Thank you, everybody, and have a great day because I understand it is day in the U.S. So.
Yes, it's still day though, at the tail end of it. So thank you, Wallace. Thank you, Aaron. That was fantastic. And as always, I've been noticing you can tell by how engaged people are in the chat. Fantastic session. Real quick about tomorrow. So tomorrow we have four sessions, starting with at 9 a.m. Central, reducing barriers to entry for new users. That's a panel. At 10:45, we have a mini talk and practicum, how to do an intake interview and then intake interviews with real researchers. Then in the afternoon at 1:30, we have the Cyber Ambassador session, Let's Talk, communicating that there's a problem, with Dirk Colbury and Shelton Carruthers. And then at 3:15 Central, we have Research Data Management, another panel. So we look forward to seeing all of you there. Thank you, everybody, for attending today. And we'll see you bright and early in the morning. Thanks so much. Bye bye, all.